So this is showing how we can use the performance packet that I provide, and in this case we're going to do the performance packet for 916 Hotel. It's pretty similar for the 172. It's 50 mic, but in this case we're just going to use the 172. So we have our empty weight pulled from the weight and balance information of the airplane. We have all our arms pulled from the same spot and also from the pilot operating handbook, and all these charts are pulled out of the pilot operating handbook. I've just kind of made it a little bit easier for students. So we've got our empty weight of our airplane, we got the weight, arm, and moment for that one, and so now we just got to figure out each station. We're given the arm, and then we'll calculate the moment and see how that does with our weight and balance. So in this case, oil. So oil will have 6 quarts. Each quart of oil weighs 1.875 pounds. So just do the math. 6 times 1.875 is going to be 11.25. Fuel, we have 38 gallons of usable fuel, so that's what we're going to use in the fuel station. And so if each gallon of fuel weighs 6 pounds, so it does, 6 times 38 is going to be how much weight of fuel we have. And so we're going to have 228 pounds of fuel. Front passengers, so let's say I weigh 155 pounds, which is about right, and let's say you weigh 180 pounds. In that case, we are going to have 335 pounds of front passengers. Rear passengers, normally my bag's sitting back there. Maybe we have some other stuff sitting back there. Let's just say we have 10 pounds of stuff in the back seat, which is where rear passengers should be. We'll say we have 0 in our baggage 1, and we have 0 pounds in our baggage 2. So we've got all the weights, and so now we can multiply the weight by the arm to get all our moments. So 11.25 times negative 14 is going to be negative 157.5. 228 times 48 is going to be 10,944. 335 times 36 should be 12,060. 10 times 70 should give us an answer of 700. And then 0 times any number is going to be 0. So we'll put that right there. So now we can add up all our weights and then add up all our moments and chart them. So if we add up our empty weight plus our oil plus our fuel plus our front passengers plus our rear passengers, and since we have nothing in the baggage, we're going to get an answer of 2,035.45. So that's how much the plane and everything inside of it will weigh. If we add up all our moments, including our empty moment, so 56,000 plus, well, in this case actually minus 157 plus 10,094, we will result in a moment of 8,317.44. So that is our takeoff total, and our takeoff moment. So we've summed up all the weights, all the moments. We can divide the moment by 1,000. So in this case on the chart, it's going to be 80. There's not a place for 80,000. And then we'll locate the weight and moment on the chart. So I'll try to annotate it here. And so if we're 2,035, we're probably going to be about here on the y-axis. And if we're 80, we're just going to be right up from here. So let's go up 80. And we should be right about here. And it didn't take. Let's see if I can get this to take. All right, we're going to be right about there for takeoff. So now let's say that we figured out that we're going to fly somewhere for an hour, and we're going to burn 7 gallons of fuel in the hour. So in that case, we're just going to burn 7 gallons of fuel. Each gallon of fuel still weighs 6 pounds. Nothing changed about that. So 6 times 7 is going to be 42. So we're going to have lost 42 pounds by the time we land. And in that case, our new weight will be 1,993.45. Similar deal for a moment, so we can just take our weight times our arm and get our new moment. Well, we can get what we need to subtract on our moment. So negative 42 times 48 is going to be negative 2016. And then if we subtract 80,000 minus 2016, we will have a new moment of 78,301.44. And so we can plot this as well. And so if we're going to plot this, we're going to be right below the 2,000 number over here on the y-axis. On the x-axis, we're going to be right here at 78. So let's follow this thing up right below 2,000. And so that's where we were right there. All right, so in both cases, we are inside the normal category. So all we care about is that we are inside of these 2 black lines. So here's our aft CG, here's our 4 CG, and if we weigh too much, we would be out there. So it does not matter the difference between utility and normal category. So we are good. Our weight and balance passes the test. So now we're going to go on to some rest of this stuff. So some of this stuff, the stuff in bold is the stuff that we're going to have to calculate based on the charts, and the stuff not in bold are things that we might need to look somewhere else for. So we got to figure out the pressure setting and the temperature. So to do that, what we're going to do is we're going to look at the METAR for the airports. And in this case, I'm going to do the calculations for taking off out of Tuscaloosa and go into Shelby County, the two airports that I'm going to use for this. So we're going to aviationweather.gov, and whenever we're there, we can just hit METARS right here, or we can go to observation in METARS. Does not matter. We'll just hit METARS right here in this case, and we're just going to put in the IDs. So KTCL, I'm going to put a space, and KEKY is the identifier for, sorry, it's actually KEET is the identifier for Shelby County. We're going to get the raw. We don't need to include the TAF this time. We're going to get it. So Tuscaloosa on the 31st at 1953 Zulu. The winds were 300 at 13, gusting 21 knots. Visibility 10. Overcast at 2,800 feet. Temperature 8. Dew point 02. Altimeter setting 3021. So now we can go back to our sheet over here. So temperature we said was 8, and we said our pressure setting was 3021. I've already done the math on a sheet of paper earlier, so and I pulled the numbers earlier. We're going to say the pressure setting that we looked at was 30.19, not that 3021, just so that I don't have to do this math really quickly while we're going along. So that's our pressure setting, that's our temperature, and we'll calculate our pressure altitude here in a minute. So let's go ahead and look at Shelby counties. So 31st at 20:02 Zulu, auto-generated 310 at 11, gusting 18 knots. It's pretty bad weather. Pretty bad day for weather. Few clouds at 800 feet, overcast at 1,500 feet. Temperature 6, dew point 4, altimeter 3015. Similar deal, I already have these numbers, so we're going to act like what I read right there was a pressure setting of 30.12 and a temperature of 7 degrees Celsius as well. So to calculate our pressure altitude, what we've got to do is we have the formula right here. Standard minus current times 1,000 equals field elevation. So the standard pressure setting is 29.92. And we're just going to subtract the current pressure setting, multiply by 1,000, and we get our field elevation. So 30.19 is going to be the current pressure for Tuscaloosa, 30.19 times 1,000 plus the field elevation. So field elevation at Tuscaloosa is going to be 170. If we plug that in a calculator, we would get an answer of negative 100. And so if we did it landing there, pressure setting 30.12 times 1,000, and then we're going to get field elevation 586 there at Shelby County, and we're going to get an answer of 386 when we plug that into a calculator. All right, so we can take these numbers. So for Tuscaloosa, which is going to be our takeoff, we're going to be negative 100, and for landing, we're going to be 386. Aircraft weight, we figured it out earlier, and the aircraft weight was, for takeoff, it was 2,035, and our landing weight was 1,993, and if we scrolled up, we could see that. And I guess if we round it up, it's actually 994, and then it's actually 36, but really it's not going to matter. So now we can figure out our ground roll for takeoff. So aircraft weight, 2,036, pressure altitude, negative 100, temperature 7. So if we go to the next page on the document, here are our options for this. So takeoff distance, it's assuming some certain conditions, and we have decreased distances 10% for each 9 knots of headwind for operations with tailwinds up to 10 knots, increased distances by 10% for each 2 knots. Where distance has been deleted, climb performance cannot be done, and for operations on dry grass runways, we'd have increased distances by 15% of the ground roll figure. If that applies, I have the answer on how we can do that on all these, for all of them right there. So in this case, we weigh 2,035 pounds, so we'll just use 2,100 as our weight. And it was 7 degrees Celsius, and we were below sea level. So sea level is the last one listed. So in this case, 7 degrees Celsius, so let's just use sea level, and let's use 10 degrees Celsius. So in this case, our ground roll is going to be 680, and our total distance to clear 50-foot obstacle is going to be 1210. So let's go up here. Let's go. We said 680, and I believe 1210. And so now we can do the same thing for landing. So weight, not going to matter for this, but it's almost 2,000 pounds. Temperature is going to be 7 degrees Celsius, and pressure altitude is going to be 386. So 386 and temperature of 7 degrees Celsius. So we have that standard weight. That's why I said it didn't matter. We still have to do something with winds, and same deal with ground roll figure if that applied. So 386. So we're somewhere between sea level and 1,000 feet. And we'll use the 10 degrees Celsius column. So this time we're going to kind of interpolate what the answer is. So how we're going to do that is we're going to use something called the interpolation formula. And you can Google it to kind of get a little bit more in-depth explanation of it. But we can just do it to try to calculate any 2 points, an estimate between any 2 points. So in this case, and the formula for it is going to be y minus y1 equals y2 minus y1 divided by x2 minus x1, and then multiplied by x minus x1. We're going to solve for y, and we know what x is. X is going to be our pressure altitude at 386. And so our x's are going to be our altitudes. Our y's are going to be our ground roll figure, and then if we recap, and then if we did the formula again, it would be our total distance clear for each obstacle. But just as, kind of double check our answer, we're going to be somewhere between 310 and 530 on the ground roll figure. Total distance to clear 50-foot obstacle is going to be somewhere between 1235 and then also 1265. Trying to get my sheet out so I don't mess up any of these numbers, and I got some of that math written down. So those are going to be between our two numbers. So if we want to just guess, 386 is about 400, which would mean that we're going to be somewhere kind of 40% greater than this number right here. We'll be kind of like 40% between the difference. And so, we're kind of 4/10 of the way there. There's a 20-foot difference on the ground roll figure between the two. And what's 40% of 20? We can plug that in our calculator, but we can kind of do it in our heads. What's 10% of 20? 2. To get a 40%, 2 times 4. And we will result in 8. So I bet our answer is going to be about 518, but we'll see what our interpolation formula gets us. So in this case, I'm going to try to draw it out, and I'm going to give us a rectangle. So we have a rectangle, and we're going to kind of have two rectangles in between it. And so two rectangles in between it. Alright, so I'll just draw this then. Alright, so it's easiest to just kind of draw out something. It'd be easier on a sheet of paper, but it's hard to do it. Let's go. Draw. Alright, we're going to draw a box. What this box is going to have is our x and our... So this column is going to be our x. This is going to be our y column. And we're going to split it again. This is going to be our 1. And this is going to be our 2. And so, I guess it would have been easier to do that with text. So, our x1, which is going to be this column right here, is going to be 0. It's sea level. Our x2 is going to be 1,000. Our y1 is going to be 510. And our y2 is going to be 530. So, now we can plug in the formula, and we know what x is. We know x is our pressure altitude of 386 we calculated earlier. So, if we set up our formula, we're going to be y, which we do not know, minus our y1. Our y1 in this case is going to be 510. So it's going to be 510, and that's going to equal our y2 minus our y1. And so our y2 is going to be 530. So we're going to go 530 minus 510. And I'm going to delete one of those. All right, let's start back over. All right, so it's going to be y minus y1, which is going to be 510, equals y2 minus y1, so 530 minus 510. And then we're going to divide that, so really I should put some parentheses around here for order operations. We're going to plug it all in the calculator at once. And we're going to divide that by x2, which is 1,000, minus x1, which is going to be 0. And then we're going to take all that, which I guess I'd need another set of parentheses if I was really going to put this in the calculator. And then we are going to divide all that. We're going to multiply all that by our x, which we know, 386, minus our y, our x1, which is going to be 0. So if we deduce this, 530 minus 510 is going to be 20. 20 divided by 1,000 is going to give us 0.02. 0.02 multiplied by 386 is going to give us 7.72, and then we can add the 510 to move it back over there, and it's going to give us an answer of 517.72, and I was pretty close to my 518 estimation. So we can kind of do the similar deal to just estimate an answer for our total distance clear 50-foot obstacle answer. So it's going to be between 1235 and 1265. There's a 30 difference. So once again, kind of we want to figure out what is 40% of 30. We can put it in a calculator, but 10%. And then if we do take that 10% and multiply by 4, we'll get the answer. So 10% of 30 is 3. 4 times 3 is going to be 12. And so that's going to give it, we're going to add 12. We're going to add to it. And so, is my math right? Yeah, 3 times 4. Yeah, that's going to be 12. And so 1235 plus 12 is going to be, what, 1447? And so it's going to be 1247. 1247. Let's go 1247, and then our ground roll figure we said was going to be 518 if we round up. So that is that one. So time, fuel, and distance to climb is the next one we have to figure out. So let's say we're going to fly this one, and let's say 3,500 was the proper altitude. And so once again, we're going to go to aviationweather.gov and just figure out what the temperature is with our winds aloft. So we go forecast, winds and temps, letting it load. All right, so it's the whole entire United States. We got to drop this flight level down, all the way down to kind of 3,000 is going to be our best estimate. And we're going to zoom in, and I'm going to drag it over to the state of Alabama. We're going to let our stations load, and we're going to have 4 stations for Alabama, and I'm going to pick the Birmingham station, waiting on it to load. My internet's slow with this rain. All right, I'll show you another way we can do it. So since that thing's not working, what we're going to do is we're going to go winds and temps data. And we're going to get the raw form that it pulls from the, like on your written test that you kind of have to do. So we're going to be South Central is going to be where Birmingham exists. And we're going to pull it up. So here's Birmingham Station. At 3,000 feet, it's 340 at 23 knots is what the winds are. So the first 2 digits are direction. The last 2 are our velocity. And if there was the plus 02, that means it's 2 degrees Celsius at 6,000 feet. And in this case, it's minus 2 degrees Celsius at 6,000 feet, wherever FSM is. So in this case, we have no temperature for that. So one thing we could do is we could assume the standard lapse rate, which is going to be 2 degrees Celsius per 1,000 feet. And since we're going up 3,500 feet, we could take 3.5 and multiply it by 2. And so 3.5 times 2 is going to be 7. And our temperature is 7 at the surface. So if we subtract 7 from it, we're going to be pretty much at 0 degrees Celsius. So we'll just say that that's the answer for that. And that's close enough. So 0 degrees Celsius, and we're going to figure out our climb, true airspeed, time to climb, fuel to climb, distance to climb. Once again, we have a formula. We have a chart for this. So time, fuel, distance to climb. One thing we got to keep in mind is we got to add 1.1 gallons for engine startup, taxi, and takeoff allowance. And we would have to increase the time, fuel, and distance for 10% by 10% for each 10 degrees above Celsius. So pressure, altitude. So we're going to cruise at an indicated altitude of 3,500. That's at least close enough to our pressure altitude. And we can't really interpolate what the difference is. So if we kind of just imagine drawing this stuff between it, and I don't know how well it's going to work out, in this case, it would kind of result in numbers between these just like this. So kind of 74, probably 500 is between our rate feet per minute. And you don't necessarily have to do this. I'm just kind of showing you. Between what's right in between 1.1 and 1.5, I bet it's 1.3. Yeah, that actually checks out. And 8 on our distance. So I kind of just wrote that there versus using this. These are just here for your own use. So climb true airspeed is going to be 74 knots. It's going to take us 6 minutes. We're going to burn 1.3 plus our 1.1 gallons. So we're going to burn 2.4 gallons total in the climb by the time we get up to our climbing altitude. And we're going to be 8 miles. So we can scroll back up here. And in this case, you just flip your sheet over. And we said our climb true airspeed was going to be 74 knots. We said our time to climb was going to take us 6 minutes. We said our fuel that we're going to burn 2.4. And our distance to our climb, we said it was going to take us 8 minutes. Last one we got to calculate is our cruise performance. And so cruise performance, we kind of, once again, we know that, so standard temperature is going to be 15 degrees at the surface. But as we climb, the temperature is going to drop. And this chart kind of has our standard temperatures right here. So, 8 degrees Celsius would be standard temperature. It is 0, we think, at 3,000 feet. So we're kind of, right here between 20 degrees Celsius below and standard temperature. So what we want to do for picking a number, we want to pick a percent brake horsepower of 65, or a number close to it. And it's just because that's what most people are going to cruise at. They're going to naturally kind of pitch their nose, fly in airspeed, pull their throttle back to hold their altitude, and be flying a percent brake horsepower around 65%. It's just a number that works out pretty good. So if our number choices are going to kind of be 65, 107, and then 7.3, and then if we're going to be 68, which we could pick 61 or 68, but it's a little bit safer looking at the gallons per hour if we pick the 68 number. So in this case, our percent brake horsepower is going to be between 65 if we are at 20 degrees Celsius below standard temperature, and 68 if we were right at standard temperature. Our knots true airspeed is going to be between 107 and 111, and our gallons per hour is going to be between 7.3 and then 7.5. So 7.3 and 7.5. That also means if we want to check what our percent brake horsepower probably is whenever we get up there, we're going to be somewhere between 2,400 and 2,500 RPM. So we could say, RPM is going to equal to 2,450. And I kind of put that in a bad spot. So that's going to be our RPM. So let's say this is going to be 67. This is going to be not true airspeed, it's going to be 109, and this is going to be 7.4. Those are kind of numbers right in the middle. Since if we were 10 degrees Celsius, we'd be right between those two. So RPM, we said was going to be 2,450. Our percent brake horsepower, we said was going to be 67, maybe 66, might be a better one. Our knots true airspeed is going to be 109. That's what we kind of figured out, and we said we were going to burn 7.4 gallons at cruise. So that's all that this really chart. That's all that we really have to calculate for most of our flights, but I'll kind of show you what the rest of these charts are at the back. So we have a range profile and endurance profile, so how long we can make on 38 gallons of usable fuel. So if we use that 65% rule again, if we just call it our 65% horsepower, if we're going to 3,500 feet, I guess we'll be right here. And if we read right down, we're going to go, 475, almost 480 nautical miles. 65% power going up to 3,500 feet. Once again, we're kind of right here. And we're almost 4.5 hours of endurance. I guess that would be 4.5. So we're probably 4 hours and 25 minutes of fuel. And both of these assume that we still have some amount of reserve of 4.3 gallons. Density altitude chart. So we can use a chart or a formula to figure out our density altitude. Density altitude formula is going to be pressure altitude plus 120 times outside air temperature minus standard temperature. I have a standard temperature column right here, but also the time, fuel, and distance to climb chart kind of had it for you as well. So if we want to figure out our density altitude, we could, let's say that we have a pressure altitude of, we figured out for Tuscaloosa was negative 100. We figured out that, and then if we solve for this one, we're going to be 120 times our outside air temperature, we said was going to be at the surface of Tuscaloosa. We said it was 7 degrees Celsius earlier. The standard temperature that it should be is going to be 15. And so well, that was supposed to be 120, not 10. So if we did, since order operations, so 7 minus 15, we're going to multiply that by 120 now. And then we're going to, in this case, actually subtract another 100 because we're adding our pressure altitude to negative 100. So our density altitude on a day like today is negative 1,060. We could do that also with the chart, just kind of double checking my answer right here. And so we're right at sea level, maybe right below it at that negative 100 number, and we can follow that up to our temperature column. Well, actually, we don't really have any following to do, and this column, doesn't go down as low as we are because we're really right here. But that does kind of check out math-wise because that's probably about where we are now. That's probably about a negative 1,000. So that checks out. So how we could also use the wind component. And so I forgot what the METAR had for Tuscaloosa, so we'll go back and pull it up just to give us a live example because it is definitely a windy day. And we're going to figure out what the wind component is. So what we need to do is we need to know what the winds are and what runway that we would land on. So I'm just going to pull up the winds for Tuscaloosa. And in this case, the winds are 300 at 13, gusting at 21 knots. So on a day like today, we probably land on 30, but let's say for this sake that we're going to land on runway 22. So if we're landing on runway 22, so if we are landing on runway 22, let me delete that. So if we're landing on runway 22, it's going to equal a 220. And the winds And the winds right now are coming out at 330. And they're coming at 13 gusting 23, I believe. Yep, 13 gusting 21. 13 gusting 21. So in this case, we have an 80 knot wind angle between our runway and the wind. So what we do is we would figure out our 80 degree looking at this. So angle between wind and runway. So we're going to go to 80 right here. And then we're going to read our wind velocity. So 80. And if the winds were actually just at 13 knots, then I guess we'd be kind of, right here between our 10 and our 15, maybe right there. And so it looks like reading down, it looks like we'd have about 12 knots of crosswind. And it looks like we would have about 12 knots of crosswind more or less. And we'd have, barely any headwind going on. But let's say we're going to be 23 knots. So now we're following our 80 out to 23. Now we have, probably a 23 knot crosswind. And now we're still only about a 4 knot headwind, which is why we wouldn't land on 2-2 on a day like today. So that is how we can use all of those charts out of our pilot operating handbook. And I just put them easily into the performance chart calculations for you.